Hello everyone, so welcome to the second hour of optics, and in this hour we are going to talk about spherical mirrors. The most important thing we are going to learn in this hour is the position of image for every goddammit position of object. Where the image will be formed, what will be its nature, the image will be magnified or diminished. And towards the end of this hour, I will tell you to use the Newton's formula to find the image for spherical mirrors, which I personally use. But as always, I will start this hour from the very basics. So without wasting time, let's start this hour. The first thing we are going to focus on is what exactly is a spherical mirror. So it's a part of a transparent hollow sphere whose one surface is polished. What is this? Think of a transparent hollow sphere and cut some part out of it. So if you cut a part out of a transparent hollow sphere, you will get this type of surface, and that will look something like a contact lens. Now, once you have cut it out, you have got two options. Either polish the outer surface. When you polish the outer surface, the type of mirror you get is called concave mirror. Or once you have carved it out, you can then polish the inner surface. When you polish the inner surface, the type of mirror you get is called convex mirror. So let's say we have polished the outer surface. When we polish the outer surface, the type of mirror we get is called concave mirror. Before moving on, we need to understand some terminologies related to spherical mirrors. So the first term we need to focus on is called center of curvature. What exactly is center of curvature? Center of curvature is the center of the sphere from which you have developed this spherical mirror. So the center of the sphere of which the mirror is a part of. The second terminology we need to understand is called radius of curvature. Radius of curvature is simply the radius of the sphere from which you are cutting out this spherical mirror. So radius of sphere which mirror is a part of. The next terminology we need to understand is called pole. Now what exactly is pole? So think in 3D. Once you have cut out a part, the type of surface you get is something like this contact lens. And to get the concave mirror, you have polished out the outer surface. Now think 3D. The center of this reflecting surface, on the curved surface is called the pole. So what is pole? You say that the pole is the midpoint of the mirror or the center of the reflecting surface on the curved surface is called the pole. The next terminology we need to understand is called principal axis. Now what is principal axis? Principal axis is this line joining the center of curvature and the pole. So what is principal axis? Principal axis is a line passing through the pole and center of curvature. There is one more definition of the principal axis. If you think of a sphere and you draw tangent at any point on the sphere, then the normal has to be perpendicular to it. Yes. So the normal for a sphere passes through the center of the sphere. So one can even think of the principal axis as the normal drawn on the spherical mirror at the pole. So if you have a spherical mirror and you think of its pole and you think of the tangent at the position of pole, and then you think of the normal passing through the pole, then this normal is nothing but principal axis. Till now, I have talked only about concave mirror, but the same terminologies work even for a convex mirror. So if you have a convex mirror, if you polish the inner surface, still the same terminology works. What is center of curvature? The center of the sphere from which you have developed this convex mirror. What is the radius of curvature? The radius of the sphere from which you have developed this convex mirror. What is pole? The center of the reflecting surface on the surface. And what is principal axis? You can think of two definitions of principal axis. The normal on the spherical surface at the pole, or the line joining the pole and center of curvature. Here you can see that we have marked a point called focus. And you must focus on focus because this is important. So let's understand the location of focus. To understand the location of focus, let's say we have got this spherical mirror. To make you understand, I have used a concave mirror. Now this central point on the reflecting surface is pole, and as you can see that this line is the line joining the pole and the center of curvature, so this line has to be the principal axis. Let's say a ray of light is hit on this spherical surface, and this ray of light is parallel to the principal axis. Then we know that once the ray of light hit, after reflection, it will go somewhere here. And this ray of light cuts the principal axis at a point. The point at which the reflected ray cuts the principal axis, that point is called the focus. Now question comes, our mission is to find the location of focus. So how to determine where is this point? So as to find this point, first think of the center of curvature of this spherical mirror. Now let's say this focus is at distance x from the center of curvature. Now बच्चों, visualize a normal at the point of reflection, because we need to apply the law of reflection. The angle of incidence is same as the angle of reflection, and the angle of incidence and angle of reflection are measured with the normal. If I draw the normal at this point, we know that the normal will pass through the center of curvature. So visualize the normal. And let's say, kids, this angle is theta. So if this angle is theta and the incident ray is parallel to the principal axis, so these two lines are parallel and this is the transverse. Hence this angle also has to be equals to theta. Now this is incident ray. This line joining the point of reflection to the center of curvature is the normal, and this is the reflected ray. From the law of reflection, we know that the angle of incidence has to be same as the angle of reflection. So kids, we can say that this angle also have to be equal to theta. Now our mission is to find the location of focus. So our mission is to find at what distance x from the center of curvature this reflected ray will pass. To find this, you can see that we have got an isosceles triangle here. Sir, how do you know it's isosceles? Better, these two internal angles are equal. That's why this triangle has to be isosceles triangle. Moreover, we know that this length is nothing but the radius of the sphere from which we have developed this spherical mirror. So this distance is nothing but r. If we drop a perpendicular, then we know that this perpendicular will bisect the length of the radius. So this length has to be equals to r by 2, as well as this length has to be equals to r by 2. So once we have dropped the perpendicular and we know that this length is r by 2, game over. Why? Because now we have got this right angle triangle. We know the base length of this right angle triangle for this angle theta, and our mission is to find x. So if we visualize the right angle triangle, for this right angle triangle, the hypotenuse is x. The base length is r by 2, and the angle made by the hypotenuse with the base length is theta. So what is the relationship between x, theta and r by 2? We can say that x cos theta has to be equals to r by 2 and game over. Hence the distance x has to be nothing but r by 2 divided by cos theta. Now do understand one important thing. The type of rays we are going to discuss in spherical mirror are special type of rays. Not all rays which are parallel to the principal axis after reflection passes through the focus. Only near parallel rays after reflection passes through the focus. What is the meaning of near parallel rays? The name itself says near parallel. The rays which are parallel to the principal axis and which are near to the principal axis. For such rays which are parallel to the principal axis and near to the principal axis, if you think of the angle theta, that angle theta is going to be small angle. So we know that for near parallel rays, the angle theta has to be small. So we can take it to be like 0. And we know from the small angle approximation that for small value of theta, sine theta can be approximated to be nearly equal to tan theta can be approximated to be nearly equal to theta. And for small value of theta, cos theta can be approximated to 1 because cos 0 is 1. So for small value of theta, cos theta can be approximated to 1. So beta, as theta tends to 0 for near parallel rays, we will say that cos theta can be approximated to 1, and when you substitute here 1 in place of cos theta, you get that x equals to r by 2 divided by 1, and that is equals to r by 2. So if a near parallel ray is incident on a spherical mirror, then after the reflection, the ray cuts the principal axis at a distance r by 2 from the center of curvature. And we know that the distance between center of curvature and pole is nothing but r. So how beautiful is this, that the reflected ray passes exactly midway between the center of curvature and pole. The reflected ray cuts the principal axis exactly midway between the center of curvature and pole, exactly at distance r by 2 from the center of curvature and at distance r by 2 from the pole. So do understand this. Hence, near parallel rays after reflection passes at a distance r by 2 from the center of curvature, and this special point through which the near parallel rays pass after the reflection is called focus. Now let's talk more about the location of focus. Let's say we have got this concave mirror again. We have just learned that the near parallel rays after reflection from this spherical mirror passes through a special point, and this special point is called focus. This point focus is exactly midway between the center of curvature and the pole. So the distance from both center of curvature as well as pole is r by 2. But what if the incident rays are not near parallel? Let's say they are at some distance. Then after the reflection, the rays do not pass through the same point. They pass through some other point. And what if the rays are even wider? They are parallel, but they are away from the principal axis. Then after reflection, they pass through even different points. So understand that only paraxial rays, the near parallel rays, pass through the focus after the reflection from the spherical mirror. If the object is extended, if you have got big object, all rays do not intersect at one point, and this phenomenon is called spherical appression. For an extended object, if the rays are not near parallel rays, you do not get all the rays getting converged at a single point after the reflection. You get the rays meeting at different points after the reflection, and hence you do not get a sharp image. And this type of aberration is called spherical aberration. Now the question comes, how to remove spherical aberration? To remove spherical aberration, do not use a spherical mirror. So the solution to overcome spherical aberration is simple. Do not use a spherical mirror. So to overcome spherical aberration, use a parabolic mirror. So what is the meaning of parabolic mirror? Parabolic mirror is a mirror whose cross section looks like a parabola. For such a mirror, if you hit parallel rays over it, then all the rays after reflection passes through a single point, and that single point is called the focus of the parabola. So how do we overcome spherical aberration? We overcome spherical aberration by using different type of mirrors called parabolic mirrors. We use these parabolic mirrors in the headlights of our car. We take the parabolic mirror, and at the focus of this parabola, we place the bulb. When the light comes out of the bulb and it hits the parabolic surface, then after hitting the parabolic surface, all the rays move parallel to each other. So what we have learned here, the emphasis on this small point, that all the rays which are incident parallel to the principal axis after reflection do not pass through the focus. Only near parallel rays do. If you have an extended object, then rays after reflection will pass through different point. You won't see a sharp image, and that will be called spherical aberration. To overcome spherical aberration, we use parabolic mirrors. Now let's understand some rule for ray tracing. So the first rule goes like, an incident ray parallel to the principal axis after reflection passes through the focus. And when I am telling you the rule 1, I am telling you the rule for near parallel rays. So whether you have a concave mirror or you have a convex mirror, if a near parallel ray is incident, then after reflection, the ray passes through the focus. Do you understand, for the case of convex mirror, the ray do not cut the principal axis after the reflection, its extension does. So you will say that this point has to be focus, and where you get the extension of the reflected ray cutting the principal axis, that point is focus. The second rule of ray tracing. An incident ray passing through the focus after reflection is parallel to the principal axis. So you can tell rule 2 also from rule 1. If a ray is hit parallel to the principal axis, then after reflection it passes through focus. So if a ray is hit passing through the focus, then after reflection it is parallel to the principal axis. So whether you have got concave mirror or convex mirror, if the incident ray passes through focus, then the reflected ray is parallel to the principal axis. The third rule of ray tracing goes like, an incident ray passing through the center of curvature retraces its path. When I was teaching you plane mirror, I said that an incident ray will retrace its path given that the incident ray has hit the plane mirror normally. Then it will retrace its path. Similarly, think of incident rays coming out of the center of curvature. If you draw any line joining center of curvature and a point on the surface of the spherical mirror, then this line itself is the normal at this point. So if a ray of light passes through the center of curvature and hits the spherical mirror, at the point of reflection, it is normal to the mirror. So it will definitely retrace its path. So an incident ray passing through the center of curvature retraces its path. So whether you have got concave mirror or convex mirror, if the incident ray passes through the center of curvature, it will retrace its path. If the incident ray is going towards the center of curvature, it will retrace its path. So these are the rules of image tracing. Now we are going to talk about sign convention. And I will say that this is the most important thing in optics. Why? Because I find students doing this wrong all the time. So if you have ever done error on sign convention, listen carefully right now. Let's say kids, you have got this. This can be a lens or this can be a mirror. And this dashed line represents the principal axis. So this can be a mirror or lens. I don't want to be biased. So I am not drawing concave mirror or I am not drawing convex mirror. I have just drawn a straight line to, let's say, this represent mirror or lens. And let's say this line is the principal axis. To understand that, whenever we measure the position, we measure it from the pole. So understand that all the positions are measured with respect to pole. We take the pole as the origin. So the coordinate of the pole is taken as 0, 0. Now the direction of propagation of incident ray, whether in the case of mirror or whether in the case of lens, the direction of propagation of incident ray is taken as the positive direction. So this direction is positive direction. So all the coordinates here will be positive and all the coordinates to the left of the origin will be negative. So you will say that I have taken the pole as the origin, and in the direction of motion of incident ray, I will take the positive direction. So all these points will have positive coordinates, while all these points to the left of it, to the left of the origin, will have negative coordinates. So this direction will be positive and the direction opposite to the direction of propagation of incident ray will be taken as negative when measured from the pole. Now let's talk about the mirror formula. So what is the mirror formula? For a spherical mirror, we say that the mirror formula is given by 1 upon f equals to 1 by v plus 1 by u. I know that most of you remember this formula, but if I ask definition of u, v and f from the students, I know that 99% of students give the wrong definition. What is u? Sir, object distance. What is v? The image distance. What is f? The focal length. Never use this terminology. Do understand that while substituting u, v and f, we measure everything from the pole. the pole is taken as the origin, and the direction of propagation of incident ray is taken as the positive direction. So what is the definition of U? You say that U is the position of object with respect to pole. U is the position of object with respect to pole. What is V? Similarly, V is the position of image with respect to pole. And what is F? F is the position of focus with respect to pole. So let's say you have got this concave mirror. If you have got a concave mirror looking like this, you can't have incident rays coming from here. The incident rays must hit from the front. So this is the direction of propagation of incident rays. Now let's say you have placed some object in front of it. Do understand that we measure everything from the pole. Pole is taken as the origin. So this direction, the direction of propagation of incident ray is positive, and the direction opposite to it is taken as negative, and the pole is taken as the origin. So you will say that the position of object is negative. As well as for this concave mirror, the focus will be somewhere here. So the position of focus will also be negative. So beta, when you think of 1 by V plus 1 by U equals to 1 by F, and you said that this is the mirror formula, I have remembered it. What is U? Position of object with respect to pole. What is V? Position of image with respect to pole. What is F? Position of focus with respect to pole. And if you can substitute these things properly with sign, game over. You will get the answer every time. So let's practice the sign for these things, taking some example. So let's take the first example. In this example, you can see that you have got a concave mirror having a radius of curvature of 20 centimeter. An object is placed at a distance of 15 centimeter in front of the mirror. So this is your object. You need to tell me in the formula 1 by V plus 1 by U equals to 1 by F, which is the mirror formula, to find the position of image, what will you substitute U as, what will you substitute F as? So we have learned that the direction of propagation of incident ray has to be taken as positive. So the direction of incident ray must be this. Now bachon, you will say that I need to measure everything from pole. The direction of propagation of incident ray has to be taken as positive. So this whole direction will be positive, and this direction, if I have to move from pole, this direction will be taken as negative. Now for this concave mirror, the focus will lie somewhere here. The focus will be at a distance r by 2. So the focus will be at a distance of 10 centimeter. I am not saying that position of focus is 10 centimeter. I am not saying that F is 10 centimeter. I am saying that the distance of the focus from the pole is 10 centimeter. So what will you write? The position of object with respect to pole. What will you write? The position of focus with respect to pole. So you will say that U, which is the position of object with respect to pole, will be taken as minus 15, because I will measure everything from pole, and this is the direction of incident ray. I have to move in the opposite direction. That's why minus 15. And what will be the value of F? F is the position of focus with respect to pole. Now with respect to pole, you do not have to move in the direction of incident ray to reach the focus. You have to move in the opposite direction. By how much distance? 10 centimeter. So you will say that F is minus 10 centimeter. And if you know U and F, using the formula, you can find out the value of V. And you just need to use the formula 1 by V plus 1 by U equals to 1 by F for spherical mirrors. Let's see one more example. If let's say, rather than giving us real object, they have given us virtual object. So there must be incident rays going like this, whose extension goes and meet forward at a distance of 20 centimeter. So again, you have got a concave mirror. This time the radius of curvature is 30 centimeter, but this time they have given you a virtual object. Now what will be the value of U? What will be the value of F? So you will say that, sir, definitely incident rays must hit this surface, not from the back. So this is the direction of propagation of incident rays. We need to measure everything from pole. And to reach the object, I have to move in the direction of propagation of incident ray. So I will take U as plus 20. So U will be taken as plus 20 centimeter. Now what will be the value of f? F is the position of focus with respect to pole, and for this particular mirror having radius of curvature 30 centimeter, the focal length, the distance of focus from the pole will be 15 centimeter. The distance is 15 centimeter, f is not 15 centimeter. To reach the focus you have to move in direction opposite to the incident ray. So you will say that f comes out to be minus 15 centimeter. The next case, if you have got, let's say, this convex mirror and an object is placed 20 centimeter in front of the convex mirror and the radius of curvature of this convex mirror is 60 centimeter. Now tell me, what will you substitute the value of u, what you will substitute the value of f? So you will say that, sir, the rays come out of the object and hit the convex mirror. So this is the direction of propagation of incident rays. Anyways, the rays can't hit from behind. So this has to be the direction of propagation of incident rays. So when I start measuring the position of object and the position of focus with respect to pole, I have to take the direction of propagation of incident ray to be positive direction. So this direction will be positive and the opposite direction has to be negative. So you will say that the position of object is minus 20. So u, which represents the position of object with respect to pole, will be taken as minus 20. And f, which represents the position of focus with respect to pole, the focus will be here at distance of 30 centimeter from pole. And to reach the focus from the pole, you have to move in the positive direction by 30 centimeter. So you'll say f will be plus 30 centimeter. Let's take one more example. Let's say they have given you a virtual object for a convex mirror. How do you get a virtual object? When you have got convergent beam hitting. So the incident rays are not at all intersecting, but their extension is. So you will say that the type of object I have is virtual object. Now for this virtual object, you will have to move in the direction of the incident ray to reach the object. So you will say that the position of object with respect to pole is plus 10 centimeter. And again, for this convex mirror, the focus will be at a distance r by 2. So it will be at a distance of 20 centimeter and you have to move in the direction of propagation of incident ray from the pole. So you will have to substitute the value of f as plus 20 centimeter. I think that if you know how to write the position of object with respect to pole, the position of focus with respect to pole, and the position of image with respect to pole, using the formula 1 by v plus 1 by u equals to 1 by f is a cakewalk. A 6th class student can do it. What we need to emphasize on is the proper usage of sign. So without wasting time, let's move on and now talk about magnification. The magnification is basically defined as the size of the image upon the size of the object. So what is magnification? The basic definition goes like the size of image upon the size of object. Now when I talk about magnification, you need to focus on two things, its magnitude and its sign. So you need to focus on sign and you need to focus on magnitude. If the sign of the magnification is positive, it means that the magnification is greater than 0. Let's say 1, 2, 3, 4, 4.5, 8.6, anything but positive. It means that the image is erect with respect to object, so they point in the same direction. If the sign of magnification comes out to be negative, let's say the magnification came out to be minus 2 or minus 2.5 or minus 6.8, it means that the image is inverted with respect to object. So when you think of magnification, you need to think of in terms of two things, the sign and the magnitude. If the magnification is greater than 0, if the magnification is positive, we say that the image is erect. It means that the image points in the same direction as the object. If the magnification is less than 0, if the magnification is negative, it means that the image points in the direction opposite to the direction of the object. The second thing you need to focus on is magnitude. Magnitude tells you whether the image is magnified or diminished. If I say that the magnitude of magnification is 2, it means that the size of image upon size of object is 2. It means that the size of image is double the size of object. if I tell you that the magnification is 6, it means that the size of image upon size of object is 6. It means that the size of image is 6 times the size of object. So if you think of the magnitude of magnification, the magnitude of magnification tells you whether the image is diminished or the image is enlarged. If the magnitude of magnification comes out to be, let's say, half, it means that size of image upon size of object is half. It means that the size of image is half of that of the size of object. So the image is smaller than object. It means that the image is diminished. So just remember that if the magnitude of magnification is greater than 1, you say that the image is enlarged. The image is bigger than the object. And if the magnitude of magnification comes out to be less than 1, then the image is diminished. So let's take some example. If I say that the magnification came out to be -2, it means that the image has double the size that of object. So if the object has a height h, image has a height 2h, and the minus sign tells us that the image is inverted. If I tell you that the magnification is 1/3, you will say that the magnification of 1/3 means that the image has got 1/3 the height of object. So if the object has got height h, the image has got height h/3. And this plus sign before 1/3 tells me that the image is erect with respect to object. If I give you magnification is -5, it means that image has got 5 times the height of the object. And the minus sign tells us that the image is inverted. So this is what all we can understand from magnification. So now let's talk about different type of magnification. The first magnification we are going to talk about is called transverse magnification. Transverse magnification means that when an object is placed perpendicular to the principal axis. So let's say this is your mirror. To make you understand, I have drawn concave mirror, and think that the object is placed with its length perpendicular to the principal axis. So when you get magnification, in this case, such a magnification is called transverse magnification, or also called lateral magnification. Now the formula of lateral magnification goes like, the lateral magnification is -v/u. The lateral magnification is given by -v/u. In the mirror formula, you don't get a minus. In the mirror's magnification, you get a minus. And when you have to substitute here v and u, do substitute them with sign. So here sign is again important. If I ask you what is v here, don't say distance of image from the pole. No. Say that v is the position of image with respect to pole. U is the position of object with respect to pole. And there are more ways to write this same formula. Using the mirror formula, 1/v plus 1/u equals to 1/f. Either I can substitute v in terms of u and f, and I can get one more formula of magnification. Or using 1/v plus 1/u equals to 1/f, I can substitute u in terms of v and f here and get one more formula. So the same magnification can also be written as f upon f minus u, or it can be written as f minus v upon f. But do understand that here you need to substitute everything with sign. Here again, f means position of focus with respect to pole, v means position of image with respect to pole, u means position of object with respect to pole. If the object and image are on same side of mirror, image must be inverted. So how can you say that? See kids, if the object and image are on the same side of mirror, then let's say this is your object and this is your image. If the object and image are on same side of mirror, this means that the sign of u and v will be same. If the sign of u and v will be same, then due to the minus sign in front, the magnification will be negative. And if the magnification is negative, it means that the image is inverted with respect to object. So if the object and image are on same side of mirror, then the sign of u and v are going to be same. And if the sign of u and v are going to be same, due to the minus sign here, the magnification will definitely be negative. And if the magnification is negative, I can say that the image has to be inverted with respect to the object. So if the object and image are on same side of mirror, image must be inverted. Next point. If the object and image are on opposite side of mirror, the image must be erect. Why? If you have got object and image on different side of mirror, so let's say this is the object and this is the image. Then if for one of them you have got positive sign, then for other one you will get negative sign, because they are on different side of mirror and you measure their position with respect to pole. So if one of them have got positive sign, another one will definitely have negative sign, and due to the negative sign already fixed in the formula in front, the magnification will become positive. So how to remember? Every time I look at myself in a mirror, I see an erect image. I'm a real object and my image is virtual. So just remember that when object and image are on different side of mirror, image is erect, our everyday observation. And what we do not observe every day is that me and my image being formed on the same side. That's why I haven't seen my inverted image. Okay, so you can remember this using the everyday example of your plane mirror. One more thing I will like to talk about here. A plane mirror is a spherical mirror of infinite radius. So everything that I'm going to teach you for a spherical mirror, that can be applied even on a plane mirror if you take the radius of the plane mirror as infinity. So a plane mirror can be treated as a spherical mirror of infinite radius. Now let's talk about the other type of magnification, the longitudinal magnification. We observe longitudinal magnification when the object is placed such that its length is along the principal axis. So when the object lies along the principal axis, then the type of magnification we see is longitudinal magnification. Now it's difficult to teach longitudinal magnification for a long object. It's not difficult, but it's a lengthier process to find it. Let's say we have a concave mirror and we have placed an object along the principal axis. Let's say the two extremes of this object are called A and B. Now how to find the magnification for this case? So beta, you will have to find the image of A. Let's say the image of A is found somewhere here, call it A dash. Since A is on the principal axis, the image of A, which is A dash, will also be on the principal axis. Similarly, find out the image of B, and let's say you get the image of B here, and let's call this point B dash. Now the distance between A dash and B dash will give you the length of the image, and the distance between A and B gives you the length of object. So if you need to find the longitudinal magnification for an extended object, you have to find the image of its two extremes. By finding the image of its two extremes, you can find the length of the image, and then you will use the magnification formula, as the magnification is nothing but length of image upon the length of object. And since this is a lengthy process, these type of questions do not come in question paper. So which type of question comes? They will ask you longitudinal magnification for a small object having a small length placed along the principal axis. So for a small object, how do we find the longitudinal magnification? From the mirror formula, we know that 1 by v plus 1 by u equals to 1 by f. Now we can write this as v raised to power of minus 1. In place of 1 by u raised to power of minus 1 equals to f raised to power of minus 1. Now but to differentiate out here each term. We know that differentiation of x raised to power of n is n x raised to power of n minus 1 into dx. So if you differentiate out each term here, you will see that differentiation of v raised to power of minus 1 will be nothing but minus 1 v raised to power of minus 1 minus 1 minus 2 into dv. Differentiation of u raised to power of minus 1 will be minus 1 u raised to power of minus 1 minus 1 minus 2 into du. And the differentiation of f raised to power of minus 1, beta, f is the position of focus with respect to pole. If the object moves, the image moves, the focus doesn't move. That's why the position of focus with respect to pole remains constant and the differentiation of any constant is 0. So on differentiating these three terms, we get minus 1 v raised to the power of minus 2 dv minus 1 u raised to the power of minus 2 du equals to 0. Now bring this term to the right hand side and rearrange it. On rearranging, you will write dv, and this v raised to the power of minus 2 can be written as v square, and there is a minus sign, equals to du upon, you can write this u raised to the power of minus 2 as u square. Now what does dv represents? Infinitely small change in the position of image with respect to pole. What is du? Infinitely small change in the position of object with respect to pole. Now from here, can I write that dv by du equals to minus v square by u square? Sir, why are you doing this? Now think that you have a point object, and this point object has got its position with respect to pole as u. If you move this point object by a small distance du, then its image will also move by a small distance dv. Our mission is to find the magnification, the longitudinal magnification of a small object. So you have a small object placed along the principal axis. So your mission is to find the magnification, your mission is to find dv by du, right? So you will say that the longitudinal magnification dv by du will be nothing but minus of v square by u square. Now we know that the magnification equals to minus v by u. So if I square it both the side, I will get the magnification square equals to minus a square. Minus a square becomes plus v square by u square. So in place of this v square by u square, I can even write magnification whole square. So we get dv by du equals to minus v square by u square. In place of this v square by u square, you can write magnification square. So you will write dv equals to minus times the magnification. Which magnification? The lateral magnification, the transverse magnification whole square into du. So you can say that for a small object, the size of image equals to minus times the magnification square times the size of the object. Now here students ask me many a times, sir, you said that magnification is size of image upon size of object. Yes. Then how dare you say that size of image equals to minus times the magnification square times the size of object? Why there is a square here? To understand what we are finding out, longitudinal magnification. What I substituted here ms, that is the transverse magnification. If the object would have been at the same distance but placed perpendicular to the principal axis, then the type of magnification I would have got, that is m here, kids. So for a small object, the size of image equals to minus times the transverse magnification whole square times the size of object. So do remember that this formula can be used only for small objects placed along the principal axis. Now why we highlighted this formula? Because this formula will be later used to find the speed of the image when the object moves parallel to the principal axis. So let's understand the velocity of image in case of spherical mirrors. Now case 1, when the object moves perpendicular to the principal axis. So let's say you have got here a spherical mirror. For the sake of understanding, I am every time using concave mirror. And let's say there is an object in front of this mirror, and this object has got a velocity perpendicular to the principal axis, and let's say this velocity is v0. So question is, what will be the velocity of the image? Now if the object has got velocity perpendicular to the principal axis, then its height above the principal axis will keep on changing, and you will say that the rate of change of height of object with respect to time will be equals to velocity of object. Now we know that if the object moves perpendicular to the principal axis, the image will also move perpendicular to the principal axis. So as we have learned that the transverse magnification is given by height of image upon height of object. And this is equals to minus V by U. The magnification is given by minus V by U. Rearranging it, height of image equals to magnification times height of object. So differentiating with respect to time, dhi by dt equals to magnification times dh naught by dt. Now bachcho, dhi by dt will represent the rate of change of height of image with respect to time. That will be the velocity of image perpendicular to the principal axis. And dh naught by dt will represent the rate of change of height of object with respect to time. That will represent the velocity of object. So from here, rearranging, you can write dhi by dt equals to magnification times dh naught by dt. So dhi by dt becomes velocity of image, and this will be equals to magnification times the velocity of object. This is the case when the object has got velocity perpendicular to the principal axis. What if the object has got velocity along the principal axis? So let's think of second case when the object moves along the axis. So if you have got this spherical mirror and the object moves along the axis, then how to find the velocity of image? We have just learned that dv equals to minus times the lateral magnification whole square times du, dividing both the side with dt. This dv by dt will become the rate of change of position of image with respect to time. This du by dt becomes the rate of change of position of object with respect to time. So that dv by dt will give you velocity of image and du by dt will give you velocity of object. So dividing both the side with time, we get dv by dt equals to minus times the lateral magnification whole square times du by dt. Now this dv by dt is the rate of change of position of image with respect to time. This is the velocity of image. And this du by dt is the rate of change of position of object with respect to time. This is the velocity of object. So if the object has velocity parallel to the principal axis, then we say that velocity of image equals to minus times the transverse magnification whole square for the same position times the velocity of object. Now these are the important things that you should know. Now moving on and talking about aerial magnification. Let's say you have got a rectangular plate of base length A and height B placed such that the plane of this rectangular plate is perpendicular to the principal axis. And you have got a spherical mirror which forms the image of this perpendicular plate. So if a 2D object is placed with its plane perpendicular to the principal axis, then you will get some magnification for its height and you will get some magnification for its width. So if you get this image, so you can see that both of them won't have the same area enclosed. So what is the formula for aerial magnification? We say that the aerial magnification, I am representing as ms because many a time we use the script s for area. Like when we write flux, we say that d phi equals to E dot ds. So we use the symbol s also for area. So we say that the aerial magnification is nothing but the area of image upon the area of object. Now bachcho, if the transverse magnification is m, then you will say that the height of the image will be m times mb and the width of image will also be m times ma. So if the transverse magnification is m, we can say that the height will be mb and the width will be m. So you can say that the area of image will be mb times ma, while the area of object will be b into a. So you can write ma times mb, this is the area of image, upon ab, this is the area of object. So you simply get m square. So just remember, if for the position of object we are getting the transverse magnification minus v by u to be equals to m, then the aerial magnification will be m square. So easy to remember because the area is proportional to length square. Hence we can say that the aerial magnification is nothing but the transverse magnification whole square, and which is nothing but the area of image upon the area of the object. So now we will talk about the most important topic of this hour. That is to know every single image position for every single object position. When the object lies between here and here, where do you get the image? Now, I will recommend you to notice the time on the video right now. And once I am done explaining the position of image both for concave mirror as well as convex mirror, come back to the same point and listen to it once more. Believe me, in an objective paper where you have got 4 options, you will be able to eliminate 2 options just by looking at the answer, that okay, image can't be found here, image can't be found there, so this and this can't be the answer. So it makes you a lot faster in the optics questions. So without wasting time, let's start learning object and image position for concave mirror. So first we will talk about concave mirror, then I will talk about convex mirror. Now if you have got concave mirror, definitely the incident ray must be on this face. So if the incident ray is here and we measure everything from pole, this direction will be taken as positive and this direction will be taken as negative. Now what we are going to do is that we are going to learn when the object moves from one position to another, how does the image move, and we will comment that what is the nature of the image. The image is enlarged, diminished, real or virtual. Just listen to it, you will get it what I'm trying to say here. Let's say initially your object is here at infinite distance. Now this side will be taken as negative side. So if the object starts from extreme left, you will say that the object starts from minus infinity. And let's say the object moves from minus infinity to the center of curvature. If the focal length is f, then the center of curvature will be said to be at minus 2f because the radius is double the focal length. So you can write in place of r 2f, and since this side is negative, you will write minus 2f. We know that when the object will be at infinity, the ray coming out of it will be parallel to the principal axis, and after reflection it will pass through the focus. So for object being at minus infinity, the image will be formed at focus, and that will be represented as minus f because it is on the negative side. And when the object is at minus 2f, we know that the ray coming out of it will be passing through the center of curvature, so such a ray will retrace its path. So for the object placed at minus 2f, the image will also be formed at minus 2f. So as the object moves from minus infinity to minus 2f, for minus infinity the image minus f at the focus, but it will be measured as negative. So for object at minus infinity, image is at minus f. For object at minus 2f, image is at minus 2f. Sir, why are you every time drawing the image inverted? Because we have learned that when the object and image are on the same side of mirror, the image is inverted with respect to object. So as the object moves from minus infinity to minus 2f, the image moves from minus f to minus 2f. As you can see that the object moves greater distance from minus infinity to minus 2f. And the image moves from minus f to minus 2f. You will say that the object moves faster, the image is real, it is in the real world, the image is diminished. Why? Because you can see that the image is closer to the mirror compared to the object for all the positions. Since the image is closer, if you think about the magnitude of the magnification, magnification is minus v by u. So since the object is at greater distance, the magnitude of magnification will be less than 1. So you will say that image will be diminished, and image has to be inverted as the object and image are on same side. Now once the object has reached minus 2f, for object placed at minus 2f, the image is also at minus 2f. The image has the same size as it is at same distance from the pole. Now if the object now further moves from minus 2f to minus f towards the mirror, as the object moves from minus 2f to minus f, the image moves from minus 2f to minus infinity. For the object placed at focus, the image will be formed at infinity. The second rule of ray tracing. If the incident ray passes through the focus, then the reflected ray is parallel to the principal axis, and such rays will meet after traveling infinite distance. So for the object placed at minus f, image will be at minus infinity. Image will be infinitely large and inverted because the object and image are on same side. So we will say that as the object further moves from center of curvature minus 2f to the focus minus f, the image moves from minus 2f, that is again center of curvature. For object at center of curvature, the image should be at center of curvature. For object at focus, the image will be at minus infinity. Now tell me this time who travels faster, object or image? So definitely image travels greater distance. It goes from minus 2f to minus infinity. So that's why the image moves faster compared to the speed of the object, and the image is real because it is being formed in the real world. The image is enlarged. Why? Because for the object being between minus 2f and minus f, the image is between minus 2f and minus infinity. So the distance of the image is more. If you think of the magnitude of magnification from m equals to minus v by u, since the magnitude of v is more than u, the magnitude of magnification will be more than 1. That's why the image has to be enlarged. And the image will be inverted as the object and image are on the same side of the mirror. Now I think that most of you know this part already. Now comes the next part from where it becomes important, and majority of students do not remember these parts. Now our object have reached already minus f. Now as the object moves from minus f to pole, the image moves from plus infinity to pole. Sir, for object at pole, the image will be also at pole. Yes. Think that you have got the spherical mirror and you get very close to the spherical mirror. So when you are very close to spherical mirror, if you zoom in on just this part, you will see yourself. And you will see this flat part of the spherical mirror, because a small part of a curve can be treated as a straight line. Small part of a curve can be treated as a straight line. So when the object reaches the pole, the image is also at pole. And when the object is at focus, the image has to be at infinity. Now just outside minus f, if the object is just here, the image is at minus infinity. But just inside minus f, the image is at plus infinity. So as the object moves from minus f to pole, the image moves from plus infinity to pole. Now to understand that, does concave mirror form virtual image of a real object? Yes, a concave mirror forms virtual image of a real object given that the object is placed within the focal length of the concave mirror. So if the object is placed between minus f and pole, you get a virtual enlarged image. As the object and image are on different side of mirror, you will say that the image has to be erect. So as the object moves from minus f to pole, the image moves from plus infinity to pole. Definitely image moves more, so image moves faster. The image is virtual, it's in the virtual world, and the image is enlarged. Why? Because the distance of image is more than the distance of the object. It has to be enlarged, and the image will be erect as object and image are on different side of the mirror. Now further, when the object is placed anywhere between pole and plus infinity. When I say that object is placed between pole and plus infinity, sir, how can you have object between pole and plus infinity? You can't have a real object. You can have virtual object. So if you have got these converging rays hitting the concave mirror. Now, bachcho, tell me, if you have got converging rays hitting the plane mirror, are they actually intersecting? No, their extension will be intersecting. So you will say that I have got a virtual object. So if a virtual object is placed between pole and plus infinity, from the ray diagram, you can understand that after reflection, these rays will move somewhere here. So which type of image you will get? Sir, we will get real image. So to understand that, if the object is placed between pole and plus infinity, to get such an object, you must have a virtual object. So if you have a virtual object placed anywhere between pole and plus infinity, it means that the type of rays hitting the mirror are converging in nature. Now to understand that, if you have got object at pole, the image will be formed at pole. Why? Because for a virtual object just behind the pole, if you look at this much part, you can say that, sir, it's like having a plane mirror and a virtual object just behind it. So the plane mirror will form real image of this virtual object just in front of it. So for the object placed at center of curvature, the image is at center of curvature. And for the object placed at pole, the image is at pole. Keep this thing in mind. For the object at center of curvature, the image is formed at center of curvature. And for the object placed at pole, the image is formed at pole. So as the object moves from pole to plus infinity, so when the virtual object placed at pole, you will get image at pole, the image will be real. When the object is placed at plus infinity, it means that the type of incident rays hitting it is parallel. Where will these rays converge? Sir, they will meet at the focus. So the image will be formed at focus. So for all the virtual objects placed between pole and plus infinity, the image is formed between pole and focus. So image is formed between pole and focus, and the focus will be written as minus f. Now again, object moves from pole to plus infinity. Image moves from pole to minus f. Who moves faster? So definitely the virtual object moves faster. So you will say that the virtual object moves faster. As the object and image are on the different side of mirror, the image will be erect. Since the distance of image is less, image will be diminished. So image will be real, erect, as well as diminished. So as I have said, beta, go back to the starting point and revise this once I am done even with convex mirrors. So now let's talk about all the image position for convex mirror. So if you have got convex mirror, again moving the object from negative extreme minus infinity to the positive extreme plus infinity. So let's take the same case. Object moves from here to there, image moves from where to where, and the comment on it. If you have got any real object, when the rays comes out of it, they are divergent rays. What will this convex mirror do to these divergent rays? It will further diverge them. So the image formed will be virtual. So remember that a convex mirror always form a virtual image for a real object. So if you have got any real object placed between minus infinity and pole, we know that for infinity the image will be formed at focus. Where is the focus of convex mirror? You will say at plus f. So as the object moves from minus infinity to pole, the image moves from plus f to pole. For object at pole, image will be formed at pole. So as the object moves from minus infinity to pole, image moves from plus f to pole. What can we say? That as the object and image are on different side, the image will be erect. As the distance of object is more and image is less, the image will be diminished and the image is virtual. And since the object moves greater distance from infinity to pole and image moves only from focus to pole, object must have more velocity. So object moves faster, image is virtual, the image is erect, and the image is diminished. So remember that for all real object, a convex mirror forms virtual image, erect image, diminished image. Virtual image, erect image, diminished image. So now we will talk about the virtual objects. As the virtual object move from pole to focus, first of all, think of the virtual object placed just on the other side of pole. So for this much part, you can think of a plane mirror and you have a virtual object. For a virtual object, a plane mirror forms a real image. And since they are on different side of mirror, the image will be erect and of same size. So as the object moves from pole to plus f, we know that the image must move from pole to minus infinity. So why are you saying that the image must move from pole to minus infinity? Because beta, when the object is placed at focus, then the image is formed at infinity, right? If you have got incident rays which are trying to go towards the focus, then after reflection, the rays will be parallel to the principal axis. and they will try to meet at minus infinity. So as the virtual object moves from pole to plus f, the image moves from pole to minus infinity. Who moves more? So definitely the image moves more. So image will be moving faster compared to the speed of the object. Second thing, as the object and image are on different side, image will be erect. The image is being formed in the real world, so the image will be real. As well as the distance of image is more, the image will be enlarged. So you will say that as the object moves from pole to plus f, the image moves from pole to minus infinity. The image moves faster, image is real, image is erect, and image is enlarged. Now let's think of the next case. We know that for the object placed at plus f, this has to be a virtual object, the image must be formed at infinity. For the object placed just inside plus f, the image is formed at minus infinity. And for the object placed just outside plus f, the image is formed at plus infinity. When the object and image will be on same side of mirror, the image has to be inverted. So as the virtual object moves from plus f to plus 2f, for plus f, the image will be formed at plus infinity. And when the object will be placed at center of curvature, the image will also be formed at the center of curvature. Now since they are on same side of mirror, the image will be inverted, but the image will have same size as for the object placed at center of curvature. The image is also at center of curvature, so the distance of image is same as that of object. So when the object moves from plus f to plus 2f, the image moves from plus infinity to plus 2f, and the image is virtual, inverted, and magnified. Image is always at more distance in this range compared to the object. So you will say that the image moves faster, image is virtual, inverted, and enlarged. Now comes the last case, when the virtual object moves from plus 2f to plus infinity. As the virtual object moves from plus 2f to plus infinity, the image moves from plus 2f to focus. Why? Because for the object placed at infinity, the image should be at focus. So when the object moves from plus 2f to plus infinity, the object is virtual, no doubt. The image will move from plus 2f to plus f. In this region, the object travels more, so object will have more speed. The distance of object is more compared to the image, so the image will be diminished. And as the object and image are on the same side of mirror, the image will be inverted. So you will say that the object moves faster, the image is virtual, inverted, and diminished. And as I have already said, now you can go back to the place where I started saying this. If you will know every goddammit image position, its nature, for every goddammit object position, you will be able to answer question way more quicker. And now comes the fun part. If you have done this part again, I again recommend, if you haven't done it, go back once. It will be just 10 minutes, do it again, and then you will be able to apply Newton's law. So now Newton's formula for object and image position. Now if the object is at distance x1 and the image at distance x2 are measured from the focus instead of pole. So if the object distance x1 and image distance x2 are measured from focus instead of pole, and we are taking beta distances, not positions now. So if the distance of object from focus is x1 and the distance of image from focus is x2, then the Newton's formula tells us that x1 into x2 equals to the focal length whole square. Now this f is not position of focus with respect to pole. This is the focal length whole square. So sir, how to use Newton's formula? Now we are going to practice 6 questions to understand Newton's formula. So let's start then. Let's take the first example. In this example, I have told you that the focal length is 10 centimeter. And there is an object placed at 20 centimeter from the pole. Without raising pen, can you tell me where will be the image formed? So using the Newton's formula, you need to take the distance of object and image from the focus. You will say that the distance of this object from the focus is 10 centimeter because from pole is 20 and the focal length itself is 10. So in x1, x2 equals to f square, or in xy equals to f square, you will say that the distance of the object from the focus is 10. We need to find the position of image. Let's say its distance is y, and this has to be equals to focal length whole square, 10 square. So you will get that y equals to 10. So the distance of the image from the focus has to be 10. So I should go from focus 10 unit this way or this way. If I go 10 unit this way, I will reach the pole. And I know that the object is placed outside the focus. When the object is placed outside the focus of a concave mirror, we get real image. So the image has to be on the same side. So that's why I should move 10 centimeter towards left. And when I move 10 centimeter towards left, I'm at the same position as the object. And isn't it obvious, if the focal length is 10 centimeter and you have placed the object at distance of 20, you have placed the object at the center of curvature. So the image will also be formed at the center of curvature. It will be of same size, real, inverted. So if you wish to use the Newton's formula, you will say that the distance of object from the focus is 10. Using xy equals to f square, distance of object from the focus times the distance of image from the focus equals to focal length whole square. You will substitute y equals to 10. Substituting x as 10 and f as 10, you will get y equals to 10. This means that you have to move this way from the focus by a distance of 10 and you will get the image there. Let's see more example to make you understand better. Now let's see this second example. In this example, you have got an object placed at distance of 15 centimeter in front of a concave mirror and the focal length is 10 centimeter. So tell me, this object is placed where? So this object is placed between f, which is at distance of 10 centimeter, and 2f, which is at distance of 20 centimeter. If the object is placed between 2f and f, the image is formed between 2f and infinity. The image is inverted. The image is real. The image is enlarged. You should know all these things just by looking at the data of the question. So I will say that the distance of the object from the focus will be equal to 5 centimeter because the focal length is 10 centimeter. So I will say that x is 5 centimeter. So using xy equals to f square, I will say that 5 into y equals to 10 square, that is 100. So y comes out to be 20. So the image will be formed at a distance of 20 centimeter from the focus. This way 20 or that way 20. Sir, I already know this way 20. And the focus itself is at distance of 10 and the image will be formed at a distance of 20 from the focus. This means that the image will be formed at a distance of 30 from the pole. So the image will be formed at a distance of 30 from the pole. I can even say, just by looking at this data without raising pen, that the size of the image will be double the size of the object, because beta the distance of the image from the pole is double the distance of the object. Magnification equals to minus v by u. Let's see one more example. Let's say you have got this case. You have got a convex mirror and the focal length of this convex mirror is 10 centimeter and you have placed an object in front of the mirror at a distance of 10 centimeter. Without even raising pen, can you tell me, for a real object, which type of image is formed by a convex mirror? So sir, for all real objects, the convex mirror forms a virtual image between focus and pole. These images are virtual, erect, diminished. Now how to use Newton's formula to solve it without using 1 by v plus 1 by u equals to 1 by r? So you will say that the object distance from the focus is 10 plus 10, 20 centimeter. So x will be 20. From the Newton's formula, we know that distance of the object times distance of the image equals to focal length whole square. So xy equals to f square. In place of x, substitute 20 and you can find out y. So you will say 20 into y equals to 10 square, that is 100. So y comes out to be 5. When I say that y is 5, it means that the distance of the image from the focus is 5. Which way? 5 this way or 5 this way? So we know that for all real objects, you get the image between focus and pole. So you have to move 5 centimeter this way. If you move 5 centimeter from the focus towards the pole, the distance of the image from the pole has to be also 5 centimeter. So you will finally find the image at distance of 5 centimeter. And I can see all this just by looking at the data in the question. And I know without raising pen, the height of the image will be half the height of the object, because the distance of the image is half the distance of the object. So if the object has a height h here, the image will have a height h by 2. Sir, I am not getting it. Do not worry. We will practice 3 more examples. So let's see the next example. This time I have given you a convex mirror and you have got a virtual object placed at distance of 15 centimeter from the pole of this convex mirror. The focal length of this convex mirror is 10 centimeters, so the focus will be somewhere here. So beta, if the focus is at distance of 10, 2f will be at distance of 20. If you have a virtual object placed between plus f and plus 2f, tell me where do you get the image? So we get the image between plus infinity and plus 2f. Since the object and image are on same side, image will be virtual, enlarged and inverted. Now how to solve? First of all, tell me what will be the value of x. So sir, focus is at distance of 10. So the distance of object from the focus will be 5. X will be 5. We know that xy equals to f square. So we can say 5 into y equals to 100, or y comes out to be equals to 20. If y is 20, from the focus, should I move 20 this way or 20 that way? So we know that for such a virtual object, this convex mirror is going to form virtual image. So we are going to move 20 that way. So that will be at a distance of 30 from the pole. Now again, just by looking at the data points, I can say if the height of the object is h, the height of the image will be 2h, because the distance of the image is double. Let's see one more example. Now this time I have taken a concave mirror. The focal length of this concave mirror is 20 centimeter. And here you can see we have placed a virtual object at a distance of 5 centimeter. Your mission is to determine the position of image without even raising pen. So tell me, if you have got this virtual object, where does a concave mirror forms the image of virtual object? So sir, when the virtual object is placed at pole, the image is at pole. When the virtual object is at plus infinity, the image is formed at focus. For all virtual object, a concave mirror form real, erect, diminished image. So sir, how to solve? See, the focus is somewhere here. The distance of focus from pole is 20. So you will say that x comes out to be equals to 25. You know that xy equals to f square. So 25 into y equals to 20 square. Once you do this, 20 square becomes 400. So y comes out to be 400 by 25, and 400 by 25 comes out to be 400 by 25. 100 by 25 gives you 4. So you get 4 into 4, that is 16. So your y comes out to be equals to 16. Now from the focus, I should move 16 this way or 16 this way. Sir, it will form image between the focus and the pole. So you should go 16 centimeter this way. And the focal length itself is 20 centimeter. We have to move 16 centimeter towards the pole. So once you move 16 centimeter towards the pole, the distance from the pole will be left to 4 centimeter. So the image will be formed at distance of 4 centimeter. And again I can say, if the height of object is h, the height of this image will be 4h by 5. Because the distance ratio is 5:4. Since the distance of the image is 4/5 of that of object, the height of image will be 4/5 of that of object. Let's see one more example. Let's say this is the case given. Here we have got a concave mirror of focal length 30 centimeter and an object is placed at a distance of 40 centimeter. So you can clearly see the object is placed at 40 and the focal length is 30. So the radius of curvature will be 60. So the object is placed between f and 2f. if the object is placed between minus f and minus 2f, the image will be formed between minus 2f and minus infinity. The image will be real, inverted, enlarged. So if you know all possible image position for all possible object position, solving the question is really easy. You can just answer them by looking at the data. So here you will say that x will be equals to 40 minus 30. So x will be equals to 10. We know that xy equals to f square. In place of x, substitute beta 10. In place of f, substitute 30. So you get 10 into y equals to 30 square, that is 900. So y comes out to be equals to 90. Now from the focus, I should move 90 this way or 90 that way. So definitely 90 this way. And the focus itself is at distance of 30. So you will say that the image will be formed at a distance of 120. And as the image distance from the pole is 3 times the object distance, I can say that if the object has a height h, the image will have a height 3h. Now, with this practice done, let's move on to the uses of mirror. So where do we use concave mirror? Concave mirrors are used as shaving mirrors. They are used by doctors as well as they are used by dentists. Why? Because when the object is placed between minus f and pole, the concave mirror forms a magnified virtual erect image. Convex mirror always form diminished image for any real object. So concave mirrors are used for shaving mirror. But to use the shaving mirror to get the virtual magnified image, it is compulsory that the object must be within the focus of the mirror. Where do we use convex mirrors? So the rear view mirror in our cars are convex mirror. So in road lamps, in side mirrors, in the vehicle, we use convex mirrors. Here is one important point that we need to keep in mind. The field of view of convex mirror is more than that of concave mirror. If you have got the convex mirror, then it can form images of larger objects placed in front of it, because from greater area the rays can fall on it. And if you have got the concave mirror, then it can form image of smaller range of object placed in front of it, because only from this smaller range of object it will get the rays to form the image. So remember that the field of view of convex mirror is more than that of concave mirror. Now this brings us to the last topic, small topic, and that is power of a mirror. So if you have a convex mirror, definitely the incident ray falling on it has to come from left. Yes sir. So you will say that for such a convex mirror, the value of f, which is the position of focus with respect to pole, will always be positive. So f is always positive. And similarly, if you have a concave mirror, then the incident ray again have to come from here. So for such a mirror, you will say that since this direction is positive and we have to measure everything from pole, so the position of focus will always be negative. We define the power of mirror as minus times 1 upon the position of focus of the mirror with respect to pole. So power of mirror equals to minus 1 by f. What is f? Position of the focus of the mirror with respect to pole. As for a convex mirror, f is always positive, the power is always negative. So we say that for convex mirror, power of the mirror is negative. And as for concave mirror, the f is always negative. You say that the power of concave mirror is always positive. So that's all in this hour. See you guys in the next hour, where we will talk about refraction of light. See you guys. Bye bye. So that's all for now. See you guys in the next hour.